A galvanic cell is based on the following reaction. Is based on the following reaction. MnO4 minus plus H plus ClO3 minus becomes ClO4 minus plus Mn2 plus H2O. Okay. A galvanic cell is based on the following reaction. Okay. Our problem is to calculate the standard cell potential for this reaction. Well, okay. Let's take a look at what we have. This is balanced as written. We can double check that. It's not a problem, but it is balanced as written because you see the H plus, you see the H2O, everything looks like it's done. Permanganate, manganese is being reduced. It's going from +7 to +2. Chlorine is being oxidized. Let me actually do this one. 10 to the 3 is 6. This is going to be +5. This is going to be +7. This is going from a +5 state to a +7, so it's being oxidized. So as written, our permanganate is being reduced and our chloride is being oxidized. So we can either read it off, or let's go ahead and take a look at the half reactions the way we've been doing so far. When we look up the half reactions in a reduction potential chart, a table of reduction potentials, we get the following. We get MnO4 minus plus 5 electrons plus 8H plus. This is exactly what it says in the chart. This is what you're looking for. Goes to Mn2 plus 4H2O. And it says that the reduction potential, standard reduction potential, is 1.51 volts. Okay? Now, the other species that we notice in there is ClO4. Well, this one, plus 2H plus 2 electrons, goes to ClO3 minus. Remember, everything is written as a reduction. Electrons are always on the left-hand side. Everything is written as a reduction in a standard reduction potential chart, plus H2O. The standard reduction potential for this one is 1.19 volts. Okay, so just by looking at these, this has a higher reduction potential than that. That means this stays as is. This reaction gets reversed. That means this is going to be oxidized to that. So when we do that, we reverse that. So let's do it. We're going to write MnO4 minus plus 5 electrons plus 8 hydrogen ions goes to Mn2 plus 4H2O, and we leave the reduction potential as is, equal to 1.51 volts. This one we reverse. We write ClO3 minus plus H2O goes to ClO4 minus plus 2H plus 2 electrons, and the reduction potential becomes minus 1.19 volts. Now, I need to make sure that the electrons balance. So I'm going to multiply this equation by 2, and I'm going to multiply this equation by 5. I'm going to rewrite what I've got. So I've got 2 MnO4 minus plus 10 electrons plus 16 hydrogen ion plus 2 Mn2 plus 8 H2O, and still nothing changes as far as the reduction potential, 1.51 volts. Here I have 5 ClO3 minus plus 5 H2O goes to 5 ClO4 minus plus 10 H plus 10 electrons. Reduction potential minus 1.19 volts. Remember, we reversed that. Now let's add this. 10 electrons cancels 10 electrons. 10H plus leaves 6H plus. 5H2O leaves 3H2O. And I end up with the following. 2 permanganate ions plus 6 hydrogen ions plus 5 chlorate ions produce, if I were to close the circuit, 2 manganese plus 5 perchlorate plus 3 H2O. And the standard rotation for that cell is equal to 0.32 volts. So there we go. If I create a cell based on permanganate and chlorate, the potential for that cell is 0.32. That means that's a measure of the tendency for this reaction to happen if I were to open the circuit. That is what's going on. Now, notice all of these species, that's an ion, that's an ion, that's an ion, and that's an ion. So when I actually draw out the physical arrangement for this thing, here is what it looks like. The cell itself is going to look like this. Going to have my digital voltmeter. And because they're both ions, okay, I'm going to have ClO3 minus, well, I'm going to leave this as ClO3 minus for right now. And I'm going to put the MnO4 minus in there. This is platinum, okay? None of these species that's been oxidized or reduced actually becomes a metal, so I can't really use that as an electrode. Therefore, I have to provide some surface for this chemistry to take place. Again, the MnO4 will go to the surface, the electrons will come, and they'll join together on that surface. It provides a platform, a meeting place for the two species. This is also going to be a platinum electrode here. This is going to measure 0.32. Okay? When we open the circuit, so again, this is measuring the pressure that the electrons, the extent to which the electrons want to go this way. When I open the faucet here, that's when the electrons are going to start to flow. When we open up the circuit, here's what happens. The ClO3 turns into ClO4 minus. So ClO4 minus starts to show up over here. This starts to go away. And MnO4 minus starts to turn into Mn2 plus. This starts to go away. Mn2 plus starts to show up in solution. That's what's going on. We can set up a standard reduction potential for any species that we want relative to the hydrogen electrode. Some are going to be positive numbers, some are going to be negative numbers, because hydrogen we set at 0. That was our choice, international agreement. Because we have now a table of all of these reduction potentials, well, I can create any galvanic cell I want just by mixing and matching species. All I have to look at is which one has a higher reduction potential. The one that has the higher reduction potential between any two species that I choose, that's going to be reduced. The other one, the equation has to be flipped because that's going to be oxidized, right? Oxidation, reduction, they come in pairs. I balance those half reactions. I add them the way that I did for the acid-base section earlier, last lesson. When I add those, I add the reduction potentials, and that gives me the standard cell potential for that galvanic cell. It gives me a measure of just how badly that cell wants to start pulling electrons. The higher that number, the higher the cell potential, the more work I'm going to get out of that particular process. That's what's going on. That's what's important. It's really, really important that you actually understand what's happening physically. If you don't get this, none of the math will make sense. Absolutely none of the math will make sense. So hopefully think about this, think about what's going on. We will do some more problems later on. Until then, thank you for joining us here at Educator.com. We'll see you next time.